We start this lecture by reviewing the concept of form or pressure drag and friction drag that was discussed earlier in connection with the laminar external flows. So you can see here that pressure drag on an object is due to pressure forces taken in the x direction. Here we assume that the main flow is in the x direction. So the component of the pressure force which acts normal to the surface taken in the x direction integrated around the entire wetted surface is pressure drag. In the same manner, the skin friction drags acts tangential or along the surface, and the skin friction stress times the tangential area, x component of that taken around the entire wetted surface gives rise to friction drag. So the two together give rise to total drag force on an object in the case of external flow. In contrast to internal flows, where there is pressure drop due to frictional forces on the wall, but there is no pressure drag. Now, it was also said earlier that these two cases, namely flat plate aligned with the flow and flat plate normal to the flow, oriented normal to the flow, represent two extremes. For instance, in this case, the drag force is entirely due to skin friction drag. Since the plate is aligned with the flow, the skin friction drag acts in this direction on the plate, and the drag force acts on the plate in this direction. So the total drag force on the plate is entirely due to skin friction drag. Note that even if the pressure gradient in this case were to be non-zero, the pressure force still acts normal to the surface, so it does not contribute to the drag force at all. So the drag force in this case, even in the presence of pressure gradient, is due entirely to skin friction drag. In this case, when the plate is oriented normal to the free stream, the flow separates from the top and bottom edges and forms a low pressure wake like this. And since the pressure is high on the front side of the plate, as the flow is turned around the plate, the pressure is high on the front side, and there is a low pressure wake on the rear side of the plate. The difference in pressure forces, which act normal to the surface of the plate, eventually result in a drag force, which acts like this. Remember, drag force acts in the same direction. It's a force on the body in the same direction as the external free stream in which the body is immersed. So in this case, the drag force is due to pressure forces alone, and it acts like this. Note that in this case, there is skin friction drag. Possibly there is skin friction drag, but the skin friction drag acts along the surface, meaning it is going to act in this direction. And so it is not going to contribute to the drag force on the plate. The drag force on the plate in this case is due entirely to the difference in pressure forces between the front and the rear side. That is the reason why it was mentioned that these two represent extreme cases, that in this case the drag is entirely due to skin friction drag, meaning only this term is present, and in this case the drag is entirely due to this term, so pressure drag alone is present in this case. And based on this, we then define bluff bodies to be objects in which or for which the pressure drag contributed a large amount to the overall drag force. In other words, in the case of bluff bodies, the drag force comes largely from pressure drag, but there can also be a non-zero contribution due to friction drag. Now, one way to reduce pressure drag in this situation, for instance, here the flat plate is shown using dashed lines. One way to reduce the pressure drag is through streamlining. Here, the front part of the object is made smooth, and the rear part of the object is also streamlined as shown here. So the object flows smoothly around, the fluid flows smoothly around this object, and the overall pressure drag is reduced. There may still be a small wake even in this case, but the difference in pressure force between the front and the rear of the object as a result of the wake is much smaller. So in this case, the pressure drag is much less than it was in this case for the same projected area. But notice that when you streamline an object, the wetted surface increases. So consequently, the skin friction drag also increases. So the pressure drag may reduce as a result of doing this, but now skin friction drag starts contributing to the overall drag force because there is a component of skin friction which acts in the streamwise direction now when compared to before. Earlier, the skin friction force acted in the direction normal to the free stream, so it did not contribute to the drag. But now there is a component of skin friction which acts in the direction of the free stream, so it contributes to drag. And the increased surface area actually increases the contribution of skin friction drag to the overall drag. So the strategy of streamlining works to some extent in the sense that it reduces the pressure drag, but it also increases the skin friction drag. Whether an optimum can be reached or not depends upon the exact shape of the object. Now, let us continue our discussion of external flow or bluff bodies. So here we are looking at flow around the sphere. The flow, the images on the left-hand side correspond to laminar cases of the same geometry, and the images on the right correspond to turbulent cases for the same geometry. The images on the top show instantaneous pictures of the flow field, and the images on the bottom show time average or mean components of the flow field. It may be seen in the case of the laminar flow that the flow actually separates just downstream of the equator, and the wake is quite large in this case. So the imbalance of pressure forces between the rear side of the sphere and the front side of the sphere can be expected to be quite large. Consequently, the pressure drag on this object can also be expected to be quite large. Although the skin friction drag is non-zero in this case, it's still much less when compared to pressure drag in this case on account of the fact that the wake is quite large in this case. Now, on the right-hand side, we see flow around the same sphere, but now the flow being turbulent. Here, the boundary layer has been tripped using a wire, which is located here. So this forces the boundary layer to become turbulent. And even the instantaneous picture shows clearly that the wake has become much more compact when compared to the laminar case. Now, the time average picture brings it out very clearly. It can be seen that the separation location has moved from just downstream of the equator to a location which is farther downstream like this, and the wake is much more compact. So it is reasonable to expect in this case that on account of the compact wake, that the pressure drag would be much smaller in this case. Skin friction drag probably is going to be higher on account of the fact that the flow is turbulent, but still the dramatic reduction in the wake size can be expected to give rise to overall reduction in drag. Let me repeat that. The dramatic reduction in the size of the wake in this case can be actually expected to give rise to an overall reduction in the drag of the object, because the pressure drag contributes the most to the drag in both these cases. And when the wake becomes so much more compact when compared to this case, the pressure drag decreases much more than the skin friction drag increases, so that there is an overall reduction in the drag in this case. So this is called drag crisis, as mentioned here, and it happens only for bluff bodies during external flow around bluff bodies. Let us explore this a little bit more. What's the reduced wake size in the case of turbulent flow? This is something that we have already discussed. So the pressure drag, consequently, in this case is much less when compared to the case when the flow was laminar. And although the skin friction coefficient or skin friction drag increases because of the flow being turbulent, the overall drag still decreases, and this is called the drag crisis. One very good example of reduction in drag due to drag crisis is the dimpled golf ball, where the dimples actually trip the boundary layer and cause the flow to be turbulent. So this utilizes the drag crisis to reduce the drag on the ball, causing the ball to travel a longer distance for a given applied force. Okay. But it is important to realize that the drag crisis does not occur for all bluff bodies. It occurs only for those bluff bodies in which the separation point actually moves as the Reynolds number or flow velocity changes. For instance, in this case, corresponding to a Reynolds number of 15,000, the separation point was located here. You can see that this is a smooth surface. And so initially, when the flow was laminar, the separation point is located over here, or the separation points are located here. And as the Reynolds number increases, eventually when the flow becomes turbulent, the separation point moves from here all the way down to this location. So only when the flow has the freedom to relocate the separation point as shown here, does the drag crisis occur. For instance, in this case, when we increase the Reynolds number and when the flow goes from laminar to turbulent, the separation locations do not change because this is a sharp edge and the flow always separates from here, irrespective of whether the flow is laminar or turbulent. So one cannot expect to see a reduction in drag force in this case as a result of transition from laminar to turbulent. So in this case, the drag is very likely to stay the same because the size of the wake will probably remain the same as the flow transitions from laminar to turbulent. Okay, notice that the drag reduction here, pressure drag reduction here is due to streamlining and not due to drag crisis. So we cannot expect drag crisis for objects for which the separation locations are fixed. We can expect drag crisis or reduction in drag only on reduction in drag due to transition to turbulent only for bluff bodies in which the separation flow can migrate from a location like this to a location further downstream. Okay, in fact, let us look at this drag chart. This shows the coefficient of drag versus Reynolds number for many objects. And if you look at this chart closely, notice that the flat plate normal to the stream, which we discussed earlier, is shown here. So the drag coefficient of drag for this geometry is shown using the solid line here. And as we mentioned earlier, the CD remains more or less constant for this geometry because the separation locations are fixed and the pressure drag and the wake size and the pressure drag does remain the same. That can be seen clearly here, and there is no drag crisis from this object. Now, if you look at a square cylinder, which is again infinitely long square cylinder, which has fixed separation points, notice that these corners are the separation flow always separates from these corners. So this geometry has fixed separation locations. The coefficient of drag shown with the dashed line here also more or less remains constant across this range when the flow transitions from laminar to turbulent. So these are geometries, bluff bodies for which the separation locations are fixed, and hence we do not see a drag crisis for these types of geometries. On the other hand, this is a smooth circular cylinder with aspect ratio infinity, meaning it's an infinitely long cylinder in a direction perpendicular to the page. And you can see that even when the aspect ratio is finite, which is shown here, we can see that in this case, drag crisis is seen when the flow transitions from laminar to turbulent because the separation points have the freedom to move further downstream. In the same manner, here we are looking at the coefficient of drag for a sphere. And once again, for this object also, you can see drag crisis where the drag suddenly reduces on account of the flow becoming turbulent and the wake becoming much more compact. Similar kind of phenomenon is seen for an ellipsoid also. Again, it is smooth, so the separation locations have the freedom to migrate downstream, and as a result, we see a drag crisis for these types of objects. However, notice that the reduction in drag is a one-time occurrence when the flow transitions. It doesn't continue beyond that. Once we go beyond the drag crisis location or the transition location, the wetted area, as can be seen here, increases, or at least the wetted area over which turbulent flow occurs increases, and turbulent skin friction drag takes over from this point onwards. And since turbulent skin friction is much higher than laminar skin friction, the overall drag coefficient of all these subjects will then start increasing once we go beyond the transition location. So the transition location, it decreases sharply, but then it starts to increase once we go beyond that because the turbulent skin friction is much higher than the laminar skin friction. However, in the case of internal flows like flow through pipes and so on, no such drag crisis is seen because there the pressure drop is entirely due to skin friction drag. And when the flow goes from laminar to turbulent, the drag force increases. So it is probably clear from our discussion so far that in the case of external flows, whether it is laminar or turbulent, and there is contribution to the drag from pressure as well as skin friction, it is not possible to develop closed form expressions for calculating CF or CD in this case. So the CD values have to be determined based on experiments or accurate numerical simulations. And these are generally reported in fluid mechanics handbooks for many different geometries. Okay, and we repeat here the definition of CD. So CD of an object immersed in an external flow is defined like this: the total drag force, which is the sum of the viscous drag force, is the sum of the pressure drag plus skin friction drag divided by half rho u square A, where A is the front projected area or the area of the object projected normal to the flow stream. So in this case, it is this cross-sectional area projected normal to the air free stream. And here again, it is area projected normal to the free stream, which is the entire plate area here. In this case, again, it is area projected normal to the free stream. So we retrieve the values for CD from fluid mechanic handbooks, and then we calculate based on the geometry of the object, the drag force, and then do other calculations which are of interest, possibly calculating the power that is required to keep the object moving at a given speed and so on. Now that concludes our discussion on turbulent external flow. We just will take up one more item which is of engineering interest, and that is drag reduction in turbulent external flows. Because turbulent flows occur so ubiquitously in nature, means of reducing drag in such flows actually is of tremendous interest in engineering applications, because that will reduce the power that is required either to keep the object moving at a certain speed, like for example an automobile or an aircraft, or it can also possibly reduce the power that is required to pump fluid through pipelines, like for example water through a pipeline or oil flow through a pipeline and so on. So drag reduction strategies or techniques for reducing drag reduction are of tremendous engineering interest. One of the ways of reducing drag, which is what we are looking at here, is in the case of turbulent external flow, is the so-called longitudinal riblets. The inspiration for these the riblets are actually triangular serrations which are etched onto the surface, and the inspiration for these riblets comes from sharks. Sharks actually, if a close-up view of sharks shows that they have these types of triangular serrations on their body, and experiments conducted by NASA show that these riblets can actually reduce turbulent skin friction by as much as 10 to 12%. Notice that this is a technique that is intended to reduce turbulent skin friction and not pressure drag. Notice that the technique of streamlining that we discuss here reduces the pressure drag, whether it is laminar flow or turbulent flow. Whereas what we are discussing now, the riblets, actually is intended to reduce the skin friction drag due to turbulent flow. Although we will not go into the details, it suffices to say that these riblets depth is of the same order as that of the sublayer, or it may be even smaller than that. So the riblets, usually these triangular grooves, have a depth of which is equivalent to about 5 plus of 5 or less, and this alter the flow in the sublayer, thereby reducing the skin friction dramatically. You may recall that the turbulent skin friction comes entirely from the viscous sublayer, and these grooves alter the flow structure in the viscous sublayer, reducing the skin friction. One difficulty with this technique is that since the grooves are so small in size, when used in practical applications, they tend to get fouled very quickly. So dirt and other things can get inside this and reduce their effectiveness very, very quickly and very, very easily. So we may wonder how sharks, which actually swim in the ocean, which is salt water, get around this difficulty. The way sharks get around this difficulty is actually quite ingenious. Nature actually has endowed them with the ability to keep shedding their skin periodically and keep growing new skin. So thereby, they keep the riblets always free of debris and falling, and continue to enjoy the benefit of drag reduction by about 10 to 12% or so. Now, this drag reduction actually is real, and there was a demonstration of this during the Beijing Olympics when riblets were actually incorporated in swimsuits manufactured by Speedo. And as a result, this resulted in swimming records being bettered by huge margins during Olympics. And eventually, the International Swimming Federation have now banned the use of riblets in swimsuits on the basis of technology doping. So this is a very convincing demonstration of the fact that riblets do indeed work as intended. Now, we now turn to drag reduction in turbulent internal flows. And here are some of the applications where some techniques have been used in the past. For example, in the transport of heavy oils, heating the oil prior to pumping actually can be helpful because it lowers the viscosity of the oil. Now, of course, we have to spend energy to heat the oil. So the economic viability of this strategy depends on how much reduction in viscosity we can achieve by heating, and the reduction in pumping power as a result of this reduction in viscosity when compared against the energy that is required for heating the oil. So there is a cost and the benefit associated with this strategy. The cost is the energy spent to heat. The benefit is the reduction in pumping power due to the reduced viscosity. So we need to balance the cost against the benefit and then try to determine an optimum temperature to which the oil should be heated so that we enjoy an overall benefit in terms of pumping power. Another technique that is used in the transport of heavy fluids is to actually introduce a very thin layer near the wall of the pipe of a lighter, lower fluid viscosity, which is immiscible with the fluid that is being pumped. For instance, if you are pumping crude oil, then we may introduce an annular layer of, let's say, water or some other lighter fluid, which has a lower viscosity, and being lighter, it floats above the oil. And since this is the fluid that is in contact with the wall, the skin friction drag in the viscous sublayer, which is proportional to mu times partial u partial y, will be less, although du dy is the same. Mu times du dy is less because mu is less on account of the fact that the lower viscosity fluid is in contact with the wall. Okay. Now, the fluid that is being pumped forms the core region in the pipe, and the fluid that we have introduced for reducing the viscosity forms an annular layer, and such flows are called core annular flows. Now, the only difficulty with this strategy is that the interface between the annular layer of fluid and the core layer is highly susceptible to hydrodynamic instabilities, and very quickly the interface cannot be maintained in the manner in which it ought to be maintained. So some detergents and other additives can be added to suppress this instability, but that is a challenge that has to be overcome for this strategy to be viable. Now, another strategy which has also been used in reducing drag in turbulent internal flow is to introduce long chain polymers into the flow. Now, the inspiration for this idea again comes from biology, where fishes are actually known to secrete mucus, which are very thick viscous substances adjacent to their skin. And the turbulent drag actually breaks up this mucus The resulting drag on the fish itself reduces, causing a reduction in external drag. So, in a similar manner, we can introduce particles made of long chain polymers into the flow, and the turbulent shear stress acting on this particle breaks them apart, resulting in a reduction in the wall shear stress and the overall drag. So these are techniques that can be used to reduce drag both in internal and external flows. This concludes our lecture on turbulent external flows and drag associated with turbulent external flows.